very basics of the noisy channel. Noisy quantum channel specifically, and then we'll slowly see certain theorem, coding theorem. Okay, certain underlying theorem in the noisy channel and the no cloning theorem property. So suppose we have a system A. Sorry. Suppose we have a system A, and we travel through or we evolve through a system which is denoted by n, which is basically a linear map A to B, and we reach to another system, say B. Okay. So if there is noise in the system, that means our quantum system is interacting with the environment. So that means A is interacting with the environment, and suppose this environment we will call as E. So then this system forms a composite system with the environment itself. And when we retrieve the information in B, there is a loss of information due to the interactions of original quantum system and the environment, right? So this is equivalent to write as the system A is passing through certain channel or certain medium, and there is some hidden measurement operator here, right? And then whatever quantum state, resultant quantum state we have, right? So how to represent this particular thing, I'll come, okay? And we get something, the system B, but there is a hidden measurement, something like that, equivalent to hidden measurement in the system because of the interactions between the system and the environment. So this NAB, this particular function, it denotes a quantum channel that takes a quantum system A to a quantum system B. Okay. So suppose that the state of a system is in the state rho. Okay. Suppose my initial system is in the density matrix is rho. Okay. Initially, system density matrix. Okay. And we perform a set of measurement operators, right? So we perform certain POVM operations, for example, the measurement operations, and the operators are MK, set of MK are the measurement operators, right? So such that we get a complete, it basically obeys the completeness relation. That means sum over K, MK dagger, outer product of the measurement operators, and their sum gives the identity, right? Like the 0 plus 1 1 kind of thing, right? Then if we do the measurement, then post measurement state will be MK rho MK dagger divided by PK. So this is like the probability. So basically this is the state, and we are normalizing that. Okay, just for that. So resulting basically so basically we can write in a different way. What is PK? PK I should define first. So PK of K is the trace of, we just defined it, right? The MK dagger, MK row. Okay, so because this is your POVM operator, we just have seen what is the probability. That was lambda j earlier, just in the previous half we have seen. This is lambda j times rho is your probability of getting the jth basis, right? Similarly, it is in the MK measurement thing. So you have MK dagger, MK is your this particular measurement operator, right? So I should write this way, and rho, right? So post measurement state will be MK rho MK dagger divided by the probability. And if there is an ensemble of many such states, right? If there is an ensemble of many such states, then we'll have an associated probability P of K of K, and MK rho MK dagger by PKK are my states. So these are now new quantum states after the impact of the environmental measurement, right? So the hidden measuring variable MK. That's I started with rho, and now I have MK is the evolution due to the environmental noise. MK rho MK dagger divided by the normalizing factor PK of K, right? And this is the associated probability. If this is my now ensemble, right? After this noise process, right? So once I have that, then I can have a evolution density matrix, evolved density matrix. That means density operator corresponding to this ensemble. Density operator corresponding to epsilon. So this part is a bit complicated. I am just covering some of the important part. But I mean, eventually it takes a whole semester to learn quantum information theory. But I'm giving a very overview of the thing. So there is much detailed proof of these intermediate steps and all. So kindly study the text material for details. So that will help us to understand the underlying theorem as well. So rho evolution is a density operator for this corresponding state. Then, of course, by the definition of density matrix, we can write rho evolution equals to summation of the probabilities pk of k times this new quantum states, right? That is the mk rho mk dagger divided by pkk. So pkk will cancel out. So we left with the summation term mk rho mk dagger. So this is so this is the evolved density matrix state. That means we started with a rho, it passes through a noisy channel, and that noisy channel has certain corruptions. That means it does certain measurement. And because of that, I get some state as a combinations, right? So that is sum over k, mk, rho, mk dagger. Earlier, without noise thing, so there is an obvious description of your state, and we had rho u rho dagger was our evolution, because that time our channel was pure channel u. Now we do not have a pure channel, we have an impure channel. So that's why we can represent the information in this way, right? Yeah, so Nelson Chuang book is a pretty much very introductory book for noisy channel, but you can go through the Wild book, Mark M. Wild book, for more details. This book is very specific to quantum informations only. Okay. Okay. So now, so this particular evolution over the noisy channel, we write it in the form n of rho as a noisy channel. It's called a noisy channel or quantum channel. Quantum channel. And it is written as n over rho equals to sum over mk rho mk dagger for k, right? So this is the noisy channel representations. Now there is a like if my environment is in the pure state ket 0, suppose special cases, for example, our environment has a pure state ket 0 E, right? Then the density matrix of the environment will be what? 0 and 0 outer product, because it's a pure state. 0 and 0 outer product of E, right? If that is the pure case, then our when we have a rho A is the corresponding quantum system, and it passes through an environment of rho E, right? So then the composite system of these two will behave as rho A tensor product of rho E, right? As simple as it is, right? And I say, okay, this together forms this system A and this system E environment together form a unitary evolution U of A E now, right? So the individual by their state description, like rho A is the density matrix for A and rho E is the density matrix for the environment. Then the evolution will be, so earlier evolution was rho via this U, we had rho A U dagger. Now instead of rho, we have a rho A tensor product with rho B, and it is passing through a unitary evolution A E evolution. Then our state will be U A E, the composite state rho A tensor product with rho E, right? U A E dagger. Now this is my representation with noisy channel. Noisy channel. This was without noise, noiseless channel, right? And this is the noisy channel. Once I know the noisy channel, there is a specific mathematical operation called the partial trace. Okay, this is a homework. This is a very easy thing. So I'm giving it as a homework. What is the definition of partial trace? Just to do it at home. It's just, if you Google it or any textbook, you will get the definition. So the partial trace, why we do use? Because I have a composite system of our system and the environment. This is a composite system, but I am not interested with the environmental noise. I am only interested with the system. So I have to trace off, or I have to find out something where I can minimize, I can eliminate the effect of E. So there is a mathematical operator called the partial trace. Now, if you take a partial trace over E, that means you are interested in finding the information of the system A. That is sigma of A. That is the representation. Okay. Sigma of A means what is the density matrix representation of the system itself, where I want to eliminate the effect of the environment. So that mathematical operation is called the partial trace operation, trace of E of this entire story. That is U of AE, rho A tensor product, rho B, and UAE dagger, right? So whatever result I will get, that is the sigma A, that will minimize the effect of the environment. Of course, you will lose certain information because of the noise, right? So this is the very fundamental aspects of quantum noisy channel. Now I'll give some examples. So take a break of 1 minute. I'll come and show you certain examples, and then we'll slowly go to the no cloning theorem. If you have any question, please feel free to put in the chat. Okay, so I found some interesting questions like what's the dimensions of these rho e and all. Practically, we don't know any dimensions, right? So it all depends how you model or how much noise you want to model. Like so basically, in a practical quantum computer, when people try to model the noise and all, they have a specified number of qubits that how much qubits I can use to specifically in error corrections and mitigation. So people take additional qubits to model the noise to eliminate their effect and all. So it all depends on your model, channel model. Okay. Okay. So let's start with some certain examples. So before the example also, I need to define something more. And this is altogether called Krauss operator. So there are certain operators called the Krauss operator or the Choi-Krauss operators. So they are the people who contributed a lot in the quantum communications. Somebody is asking what is the analog of AWGN in quantum system? Do you have Gaussian noise? Okay, I left these questions to you. You please find it as your research, right? Um, you cannot always like what to say. Uh, you cannot always assume certain particular noise model to quantum as an equivalent analog of classical. But of course, because uh, now if you try to think all your probabilistic assumptions to follow central limit theorem or certain things or ultimate randomness and also those things, um, those things are there, okay? But there are specific cases like why do you assume the AWGN in quantum system or not? So there are certain things like quantum classical channel, right? So those things are there. Okay. So I'm not covering that part, but that's a research question. So you can look at it. Okay. So now let's define some more operators. The one particular operator is called the Krauss operator. So it's basically it states that this theorem states that any CPTP, so this is completely trace preserving operator, right? So CPTP is the uh, completely trace preserving operator. So any CPTP operator, for example, so those operators which are complete mapping as well as the trace preserving. That means after the operation, the trace does not change. Okay. So you can have a look on the CPTP operators and details. So in any so a quantum channel is basically defined as a CPTP map, right? And the details you can look in any standard textbook. So basically any CPTP operator it maps basically epsilon on a state. And state by state, I mean the density matrix representation of the state rho. It can be written as, so CPTP operator map epsilon on a quantum state rho, and it is denoted as the epsilon of rho equals to sum of k small k rho k small k or any other operator I you can use dagger over small k. Okay. So this sets of operators, I can represent any quantum channel, basically CPTP map quantum channel, as a sum of this density matrix. So earlier we represented in the POVM form, POVM measurement form. Here we are representing in a special form, KK rho, KK dagger. So this set of operators KK or insert K. So K operators are known as the Krauss operators. Um, so satisfying it also satisfies the completeness relation that KK dagger KK is the identity matrix, number of operators in a measure of dimension of the environment. So the number of Krauss operators is a measure of dimension. The number of Krauss operators is a measure of the dimension of the environment that the system is interacting with. That the system is interacting with. Right? So so this just a representation, and there are more details of Krauss operator in Mark Wild book. You can see just how we represent the channel, either in terms of the noisy evolutions or in a very simple way of writing it as in the Krauss representation form, that is K rho K dagger, right? So they are the operators which acts on the Hilbert space and satisfy the completeness relation. That's the definition, right? Now, for certain various quantum channel, what is the Krauss operator and all, I'll show. One theorem for quantum channel is something called the Choikowski isomorphism, or the full name is Choi-Jamiol. Spelling might be pronunciation might be incorrect. So in short, I say Choikowski isomorphism. So this is one important note. So the isomorphism establishes one-to-one correspondence between a complete positive map epsilon and a positive semi-definite operator. So suppose there is a complete CP map. Suppose there is a CP map epsilon, and suppose there is a PSD operator, positive semi-definite operator, that is given by J of epsilon, right? On the tensor product. So it basically acts on the tensor product space between the input and output. So it is also called the Choi matrix, and it is defined as J of this epsilon equals to epsilon tensor product with identity times any quantum state phi and phi, where phi is basically, if it is a maximally entangled, is maximally entangled state. So that means I can have something like 1 by square root d summation over I get I. That means suppose for a 2-qubit system, it is 1 by square root 2 the Bell state 0 0 and 1 1. If this kind of states are there, then I can create a PSD matrix out of the complete CP map as the epsilon, that is the quantum channel tensor product with the identity matrix, times the maximally entangled state, right? So outer product of the phi state, but phi is basically something like this, right? So 0 0 plus 1 1, something like that, right? So this is just a definition. There are more formalism like Liouville super operator formalism and all. So I'm not going in this direct direction. But when I was talking with the environment, so maybe you can look at the details of this Choikowski operator if you are interested, right? But let us go to some basics again, because that is important. So in simple, what we learned, that any quantum channel we can represent in Krauss form if we know some Krauss operator K. And if we know the real density matrix representation without noise, that is rho times the Krauss operator K dagger for little k number of terms, summation of little k number of terms, right? So this is the quantum channel representation in the Krauss representation form. And let us see certain example. First example is the bit flip channel. Yesterday we were discussing these things, but now in more formal way. Bit flip channel. That means your quantum channel change the bit. suppose you transmitted a composite quantum system of 000, but you get suppose 001, right? So there is a bit flip done by your quantum channel due to noise, right? If that is the case, right? So the bit flip channel models an error whether a qubit state is flipped. That let's formally write it. So if it is if a quantum state is flipped, and the flip is like 0 to 1 or vice versa, something like that. This kind of flipping is there with some probability. Right? So this is if you want to think in comparison with the classical channel, this is very similar to something the binary symmetric channel, right? So you transmitted 0, you are receiving 0 or 1. If you are receiving 1, that means there is a error. How much? What is the probability of this error? P. If you are getting the correct bit, with what probability? 1 minus P. So this 1 to 0 and 1 to 1. So suppose, for example, it is 0 to 1 is probability P. So again, 1 to 0 is probability P, and this is 1 minus P, something like that. So binary symmetric channel, something like that. So it is equivalent to that, but not the same thing. Okay, so in this particular case, the bit flip channel is Ket0 to Ket1 or Ket1 to Ket0 with certain probability, right? This corresponds to the application of the Pauli X operator. So it corresponds to application of X operator, where X is basically your 0, 1, 1, 0. Yesterday we have seen these things. Now, if you want to model this bit flip for a large number of bit string, so there is a physical model that qubit is transmitted through a bit flip channel with probability, say 1 minus P is the probability. Nothing happens, means no error, say, for example. And if P is the bit flip error, probability of bit flip error. If that is the case here in this bit flip channel, then the Krauss operators K0, the Krauss operators are so K0 is 1 minus P, nothing changed, means identity matrix. That is also equals to we can write it as 1 minus P 1 0 0 1. This is my Krauss operator K0, and K1 equals to square root P, right? And there is a bit flip times X, right? So that means square root P 0 1 1 0, right? So these are two my Krauss operators. And now I can check the completeness relation, whether this is forming a completeness relation or not. So you just need to do summation over K dagger K, right, over little k. That is equals to K0 dagger K0 plus K1 dagger K1. If you do that, so you'll be getting square root 1 minus P I square plus square root P X square. So you'll be getting 1 minus P identity matrix plus P into identity matrix. So this will be equals to identity matrix, right? So this is giving you the completeness relationship, right? So this is the bit flip error channel, and how to represent the quantum bit flip channel is basically epsilon bit flip in the Krauss operator form of a quantum state rho, that is equals to K0 rho K0 dagger plus K1 rho K1 dagger. And we know if any quantum state, then uncertainty in a quantum state represented in the density matrix given by rho, then we can write the quantum channel with this. So this is here in this particular bit flip channel, the equation is 1 minus P times rho plus P times rho, right? This is my epsilon BP for the bit flip channel. Okay, so this is the bit flip channel. Now our homework is, suppose there is something called the phase flip channel. Yesterday we discussed about the phase flip channel, right? Now the second part is the phase flip channel. Now, can anyone say me what is the phase flip channel equation for the channel model? The phase flip PF of rho. So I'm giving 1 minute. You calculate what is K0, what is K1, right? Suppose let me give you the correct probability is given by 1 minus P, same thing. And the probability of error is given by P. Then what is K0, what is K1, and what is the channel here? Do a calculation. Pauli Z operator is given by these things. 1, 0, 0 minus 1. Just following the previous steps, do it and calculate the channel. And one additional question is, suppose my state is psi equals to alpha ket 0 plus beta ket 1, right? Then what will be my quantum channel matrix? What will be my quantum phase flip channel model or the channel matrix operator? Third question is, if psi is a maximally entangled 2-qubit state, that means this is equals to, suppose, 1 by square root 2, 1 by square root 2, 0, 0 plus 1, 1. Maximally entangled 2-qubit state, what will be my epsilon phase flip or the bit flip, in fact? So channel model for that. So these are 2-3 questions. Maybe you can give a try for 2-3 minutes, and otherwise it's a homework. Okay. I'll wait for 1 minute. So there is something called the depolarization channel. I'm just writing the equation. You can later copy these things. So depolarization channel means it's a simple and widely used channel model of noise, where the qubit state is randomly mixed with maximally mixed state, right? Such that you can represent whether the quantum information is losing or not, with what probability, right? So basically you have 4 Krauss operator, P0, K0 equals to 1 minus 3P, for example, by 4 identity matrix. K1 equals to, these are specific cases, okay? Square root P by 4, Krauss operator 2 equals to square root P by 4, and Krauss operator 3 equals to square root P by 4. Suppose this is the Krauss operator form. You can take all have certain identity, for example, matrix, right? 1, 2, 3, 4, right? So now in this particular case, I can represent the channel. Uh, uh, so you'll see just by applying the Krauss operator from the depolarization channel here in this particular case, we can model it at 1 minus P times rho, plus because of the maximally entangled part, it will be rho identity by 2. So more details are there in the notes. So like phase damping channel and other channels are there. So I'm skipping those parts. So please have a look in the notes and all details are there. So now directly we'll go to the no cloning theorem first. So I'm waiting for those who are solving the problem. 1-2 minutes maybe. Okay. So let's start the no cloning theorem part. So once this theory is done, it has a lots of implications in quantum key distribution. And because already there will be experts who will be covering those topics, QKD, BB84 protocol and other things. So we will not go details. So I'll just give examples, and maybe 10-15 minutes prior we can complete the sessions today. But kindly cooperate with that part because other experts will take on top of it. Yeah, answer is correct. So let's start with no cloning theorem. And this is the heart of any quantum security, quantum cryptography or quantum security. So the bottleneck is that I cannot copy a quantum information. Suppose in classical memory, in a classical random access memory RAM, you have some information 0, and this is vacated, right? You can copy this 0 and you can keep like here is 1 0, here is another 0. You can just make a copy function which will copy this information and put it here, right? 0 0. This is a classically this is possible that you transfer an information X, and on the AR anyone can copy this information X without, if there is no security, for example. So then this X can be copied and it can be kept in any. This is the advantage of digital electronics or digital communications, that you can copy the same information into multiple devices. Quantum does not allow you to copy the quantum state gate psi. That is not ever possible. Quantum state you cannot copy. And let us formally do this and prove it. So the bad part is that I cannot store quantum information because of their ultimate randomness, first of all. Secondly, there is a good part. If I cannot copy an information, so I can securely transmit the information from place A to B. And if anybody try to hack this information in the quantum channel, it is impossible, because if I want to measure what is alpha and beta in this state, so I have to do quantum measurement. If I do quantum measurement on the state gate size, so the state will be collapsed, right? It will become the classical information and no quantumness here, right? So many quantum security QKD protocols are there, quantum cryptography protocol are there, designed how to secure this alpha and beta or these quantum state psi, right? Using entanglement as a resource. So I'm keeping that part apart because experts will take much detailed and things on that. But we'll only discuss this, what is no cloning theorem and proof of the no cloning theorem. So I am giving a proof in my whiteboard now in one way, a slightly variant you can see in the notes. Okay, it's a bit different, but ultimately I will prove by contradiction. So what is the theorem? It states that it is impossible build a copy device or a copier device, a device which can copy. It is impossible to build a copier device that could copy arbitrary quantum state as an input. It's impossible. Okay, so let's prove this theorem. So we'll prove by contradiction. Right. So suppose there exists some unitary operator U, right? and we say which is an universal copier. Suppose I say there is a quantum computer which can copy any quantum information, suppose, right? If I say this, immediately what happens? Suppose my input state to that device U is kate psi, and I say it is some arbitrary combination, probabilistic combination with probability amplitude alpha times kate 0 plus amplitude beta times kate 1. The probabilities are alpha square beta square, but in general, it's alpha 0 plus beta 1 is the vector representation of the state in the basis 0 and 1, right? Uh, let's take in the first qubit, it is suppose it is in the first qubit, and let's take another auxiliary qubit. Suppose I take this state as 1 qubit, right? And I take another quantum memory or another quantum auxiliary qubit kate 0. And suppose I want to copy this information to here, okay, in this particular state, right? So purpose of this device is, if I apply unitary on the state psi and there is another register 0, so eventually the purpose of this device or the unitary device is to make this memory to psi. That means kate psi and kate psi. So I should start with a quantum state psi, and the purpose of this U is to make the second qubit or the register 0 to a copied version of the first register. That is psi. That is the objective of this U. Okay. So now, what is the resultant of this psi part? So this is alpha kate 0 plus beta kate 1 times alpha kate 0 plus beta kate 1. These are just a simple multiplication. And now if I complete the multiplication, I have alpha square 0, 0, right? Plus beta square 1, 1. The first term and last term. And the intermediate part are alpha beta 0, 1 plus beta alpha, beta alpha is 1, 0, right? These are the 4 terms here. Now, as kate psi is an arbitrary state, right? Then kate psi can also be kate 0 and kate 1 as well, because these are vectors, right? So individually I created the state as a superposition of two states like 0 and 1. So individually they are vectors and they are valid quantum state, kate 0 and kate 1, right, are as well, right? So hence the purpose of this U is, if I apply U 0, 0, so it will be 0, 0, right? And if I apply U 1, 0, right, so then it will be 1, 1, because this register is copying the information from here with the help of U, right, by definition, right? So then if that is the case, and suppose this is my equation number 1, right? Now then this U alpha times 0 plus beta alpha kate 0 beta 1 times kate 0, that is U psi 0. This is basically your kate state psi, right? U psi 0. Here, what you are getting, instead of writing in psi, I have written this way because I want to apply this and this. So immediately what I get, alpha 0, 0, because this is giving 0, 0, plus beta 1, 1, equation number 2. Now if I see equation number 1 and equation number 2, although the initially what I have done here and initially what I have done are the same things, but the resultant part here and here are different. That means one contradicts 2, right? So that means there are certain alpha and beta, there exists certain alpha and beta, there might be, right, certain alpha and beta, for which alpha square 0, 0 plus beta square 1, 1 plus alpha beta 0, 1 plus beta alpha 1, 0, they may not be equals to this thing. There might be some alpha and beta that is not equals to alpha 0, 0 plus beta 1, 1, right? They may not equal, right? Hence, hence linearity of quantum theory, that means superposition of quantum theory, contradicts a universal copier device. I cannot do this, right? So hence we cannot copy any quantum informations, right? So basically, if we can copy these things, so then basically this left hand side and right hand side should be equal. But in this particular case, we see this is not possible because of the linearity or superposition property of the quantum theory, right? But now, but if alpha equals to 1 and beta equals to 0, if that is the case, or alpha equals to 0 or beta equals to 1, what immediately happens? If I say that my quantum state is perfectly in the state 0 or perfectly in the state 1, right? Because I know that alpha equals to 1, beta is 0, or alpha equals to 0 or beta equals to 1. That means my information is definitely 0 and 1. That means it is classical. Once I say the information is classical, that means there is no associated probability of the bit string. Once I say that, right, then this left hand side 1 will become equals to 2. They can be equal, right? If they can be equal, that means classical state can be copied. Classical state can be copied, not the quantum state. Classical states or the classical bit string can be copied, but not the quantum state be copied, right? So this is the heart of quantum security. Okay, so it has several implications, several applications, in fact. So it underlies the quantum security, the thing is called quantum key distribution, QKT, right? Security or QKT protocol, that attackers cannot copy quantum states. Quantum state that two parties use to establish a secret key, right? So this is the beauty of quantum. In fact, the quantum no cloning theorem, that quantum information you cannot copy, right? On top of it, for specific protocol, example BB84 protocol. So if you see discovered by Charles Bennett, I shared the note. You can look at it, and later other experts will definitely cover much details of BB84 protocol and other protocols. You will see that how I can create certain state. It's a certain composite state, and that composite state may have certain amount of, or mixed state or certain amount of entanglement also. Then if I can create a party like A and B, Alice and Bob, between row A and row B, I can create an entangled state, and I cannot basically copy this state, right? I can securely pass through a quantum channel from place A to B, right? So those details are there, and I just covered all the important mathematical stuff that is required to understand the quantum channel, quantum noise, and no cloning theorem. These are the fundamentals for quantum communications. And I believe there are very good standard textbooks. You can build more skills and knowledge on top of it, and you can do further research. I have given certain directions such as tomography, modeling various quantum channels, because how it impacts the quantum information, how much information I can lose in the environment because of the noise and all. So those details are certain topics you can definitely look at. As well as this kind of knowledge are also useful in quantum communication algorithm design, specifically the error mitigation, error corrections things. So because if there is noise, now if I take additional quantum resource like qubits to model the noise, so how much noise I can mitigate up to what order, right? So with this, I conclude my session here. And if you have any questions, please feel free to ask me. So
So
some of
any
the things,
questions from
please feel free
participants?
to ask. So sorry, sir. So one thing just I forgot. So there are some more things. So those who are interested in modeling the environment. So there are associated theories like the open quantum system, the Lindblad equation or master equations and those things. So I haven't covered those part, but those who are interested, they can look those aspects as well. Yeah. Yeah. Sorry, sir. Yeah. Please continue.
No, I was just announcing if somebody has questions, they can
So most
they
of the
can.
questions on the way, I just solve, like I try to reply them. And if you have a new question, please feel free to put in the chat. We can wait for 5-10 minutes we have. So no issue.
So if participants do not have question, probably I can ask a general question like,
Yeah, please.
what exactly is currently happening related to quantum communication in industry?
Yeah. So I show the speaker list. Basically, Professor Bhaskar Katseri, Professor Anil Prabhakar, they are the leading expert in this area. So you will hear much more concrete and good answers from them, definitely. So we are like from IBM side, let me give the answer. So basically, there are two things. One is the quantum computing part. Within even computing, there are certain protocols. If you see like how the information process within a quantum chip, so there are lots of quantum communication protocols that I covered are useful. On purely communication security side, also our companies provide certain things called the post-quantum crypto or the PQC, right? So suppose you are transmitting information so from place to place right now, right? And there is a threat that if there is a large number of qubits, quantum computer is available. So my classical RSA key, right? The RSA algorithm may fail, right? Although there are like discussions, contradictions, and other things, but eventually people understand it as a threat of classical security side, right? So how without RSA can I design other classical protocol by knowing that these are various quantum channels and various quantum errors and quantum attackers may work on this part. So basically there is two part. One is the quantum cryptography and one is the PQC part. PQC is there are a good number of companies in India, including I believe DRDO is also working and many good startups. They are also working on the PQC post quantum crypto because they are designing certain device and they say, okay, this is like at least your classical communications that you are presently doing, it is like there will be no quantum threat on it, right? So this is the PQC part, post quantum crypto, as well as there is a thrust on the quantum security side on the QKD, like there are BB84 protocol and other protocol E91 and other protocols are there in the quantum communication. So people are trying to design certain cryptographic key, right, on the quantum side itself. And they try to see, okay, if I can make the quantum resource entanglement, these things as a resource, I can create a quantum key which is ultimately secure because of the no cloning theorem. Because if I can transfer my quantum information in the quantum mechanical way, like the photonic or some other way, so then basically nobody can copy my informations, right? So there is a, from industry point of view, the quantum cryptography is very, very new area, sir. So people can look at it and there is very hard, like hardly like, although QKD is very standard, but there are people are also looking for other cryptographic key. And this is a very like emerging area of research and there is hardly any good solutions exist. So there is a lot of scope of improvement and all. And this is an exciting area, QKD and the quantum cryptography, and people can look at it. And recently, IIT Delhi and DRDO also demonstrated probably last year or last to last year on a 384 or 385 kilometer cryptography keychain. They communicated information and showed the quantum advantage in the security part. So there is a lot of like happening in the quantum communication, and through this course, like we are discussing some of the basic stuff. So I hope many will be interested to dig this area more and more.
Great. Thank you. We have some few questions in the chat box. Probably some are
Yeah.
answered by the participants itself, but probably if you can have a look and if you want to answer some of them.
Yeah, sure. Okay, there is one question. Thank you so much. Request to say does and don'ts for doing a very short-term introductory project on quantum computing. For example, on simulating quantum state, etc. Your suggestions. Okay, somebody is asking on quantum computing side. No issue. So there is no don'ts. Okay, try anything. As a researcher, I won't say anything. Don'ts. Whatever you want, you try it. You design a theory, you simulate it on a quantum computer by IBM or any other company's device like Penny Lane or others. Anything, that's fine. Qiskit is very friendly one. You can try a project like simulating quantum state, quantum gate. So you can think of like phase estimation or solving linear system or financial transaction fraud detections. In fact, finding the ground state of hydrogen molecule. It can be your protein folding problem, certain discovery of new proteins for a particular disease. It can be finding the, for example, certain dissimilarity in a medical image like fMRI or ECG or like there are lots of problems. For beginners, you can start with Bell state, Grover's algorithms of these things, and slowly once you understand how these things works, you can take a real world problem and you can try it. So is there any question like input on setting up in hardware experiment? So you initially those who are very new, I won't suggest you to directly go to hardware. You try any simulator, quantum simulator. That's a classical hardware, but it knows the behavior of quantum to some extent. That means the quantum operations are defined in a software called a simulator, and you can run quantum circuit there. Once you are confident up to certain things, okay, I can run things on the simulator, then you have a real problem and you try it on hardware, because hardware actually, quantum hardware will actually give you the strength to simulate big problems which you cannot solve in a classical things. Small problems try on simulator, big problems try on hardware. Yeah, so other things like coding and also there are many Qiskit sessions like QT-125. I think, sir, they can revisit the lecture series on YouTube and you can practice those things. So I think most of the things are already answered. Yeah.
Okay. So we thank Dr. Rahman for accepting the invitation for giving these 4 sessions, and I hope that participants have started getting the flavor of quantum communication, because the last week there were many participants who were eager to jump to quantum communication before starting the classical theory. So there were questions like why are we studying these classical theory of communication system? Probably with these 4 sessions, we have started diving into quantum communication, and the future speakers which are aligned will be going much more deeper in this particular area. So I thank once again Dr. Rahman for giving these wonderful 4 sessions, and I hope the participants have enjoyed.
Yeah, thanks.
Thank you.